Today's class we are going to talk about heat equation. So next few classes we are only going to concentrate on this heat equation. Now let us start by writing out what it means. What is a heat equation? So essentially, generally speaking, we will write it like this: ut minus Laplacian of u equals to, let's say, f, right? And this f will depend on x and t. Clear? Now, so this, let me write it properly and then we'll explain what I mean by this. So this will be in some domain, yeah? We will write down all this domain and everything. But first of all, let us explore more what this means. So let's say that's your 1, okay? This is defined in some domain. Now, what is u? U, yeah, here is the unknown. And this is the unknown, yeah? Unknown function, okay, and you see here I write ut. So basically u depends on a variable t, right? Of course, because otherwise there is no point of writing ut. And I also wrote a x here, yes. So what all of this means, see, and here we assume x is in Rn. Clear? X is in Rn and t lies between 0 and infinity. Clear? So essentially, see t here, I mean this equation, this is a part of a, so let me put it like this, it is a part of something called the evolution equation, right? Evolution equation. Now, what is the evolution equation? Evolution equations are those equations which evolve with time. So over time, let's say you are modeling some phenomena which changes with time, right? Those phenomena, whatever the equation you generate with those phenomena, they are called evolution equation because they evolve with time. Okay, either they degenerate with time or the other way around. Okay, but here what is happening is this, as you can see, this equation has a ut term. So essentially this will depend on time, right? And that is why it is a part of a evolution. This is one of a evolution equation. Yeah, the other one which you will study later is called a wave equation. Okay, so let us again come back to this equation. Let's say x is in Rn, right? So for, let's say, for n equals to 3, let us assume, yeah, n equals to 3. How does this equation looks like? See, first of all, u in this case will be function of x, y, z, and t, right? Because you see, u should contain. See, okay, there is one here. You might get confused here. Let me put it this way. It is x1, x2, and x3. Clear? Where where x is given by x1, x2, x3, that is in R3. Okay, so you have a component from R3, the first 3 component, and there is a component of time. Okay, this t, see, t we are assuming from 0 infinity. So t is a time variable. So there are two kind of variables here. Okay, so let me put it this way: two variables, two kind of variables. Okay, kind of variable. What are those? Number one is called a spatial variable. Okay, spatial variable. So we'll call it a spatial variable. What is a spatial variable here? The spatial variable is xyz here. Okay, so or sorry, not xyz, x1, x2, x3. See, I wrote x is in R3 here, so that is why I can't use xyz. So here x1, x2, x3, that is the spatial variable. Okay, and there is another variable which is the time variable, right? And the time variable. So of course, whenever we are you see, working with time variable, we are assuming that this will be always positive, right? So see, we always assume that whenever we are starting out a process, we are assuming that the time is 0 at that time, and after that it is moving forward. So time t will be always between 0 and infinity, right? So this is the time variable. So this is given by t, which is greater than 0, right? So spatial variable and time variable. Okay, and now let us look at this equation. See, this equation ut is your partial derivative of u with respect to t minus Laplacian of u. This Laplacian, see, u is a function of x1, x2, x3 and t. So generally speaking, okay, in generally speaking, you see, if u is a function of x1, x2, x3 and t, okay, what is Laplacian of u? It is essentially u x1 xi sum plus u of tt, right? Okay, that should be your Laplacian, because if u looks like this, Laplacian of u, generally speaking, if it is written like Laplacian of u, it means this. Okay, but here this is not the case. Is not the case. Clear? Yes. So here this Laplacian is with respect to the spatial variable. So what I mean by this? So essentially, let me put it this way. Essentially, one boils down to this form. Boils down to the following. To the following. This is ut. Is ut. There is nothing to do here. Minus Laplacian of u is u x1 x1 plus u x2 x2. So basically this Laplacian is with respect to the spatial variable. So with respect to x. Okay, with respect to x. Okay, plus u xn xn, sorry, x3 x3. This is equals to f of xt. Right? That's your one. So this is refreshed as 1. Okay, so of course if x if you're taking x to be in Rn, then it will go on in xn, right? And then u x3 x3 plus dot 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 u xn xn, right? It will go on like this. So this is called the C. So in any of these cases, you see what is changing essentially is this x can be in R1, R2, R3, Rn, right? Yeah, but this time variable is always there in between 0 and infinity. Okay, so there is a small notation which you are going to use. So basically this is just a nomenclature, you can say. Okay, so one dimensional, we say one dimensional heat equation basically means that the dimension x varies in r. Okay, so basically x is one dimension. So basically that will look like ut minus u xx equals to 0. That's your one dimensional equation. See, t is always between 0 and infinity. So there is nothing, t does not do anything. All, whatever, if there is a change in dimension, that has to be in x, right? Okay, so that is why whenever we say one dimensional heat equation, we mean ut minus uxx. Only x variable is there. So x is in r, right? X is in r and t greater than equals 0. Okay, now if I say, let's say, n dimensional heat equation, you can understand n dimensional heat equation. Of course, it means that you write it like this: ut minus u. So let's say ut equals to, so you see here I am just assuming f is 0. Okay, here I am just assuming the homogeneous problem. Of course, if you if you do not have a homogeneous problem, of course there is a f. Yeah, that is there. So I'm just writing it to be f equals to 0 for now. Yeah, I'm just assuming f equals to 0. Here also f equals to 0 I'm assuming. Okay, so f is equals to 0 I'm assuming. It may not be 0. Yeah, in that case you just add a f. Yeah, so this is n dimensional equation is x1 x1 plus u x2 x2, and it will go on and it will be u xn xn. Clear? So that is your n dimensional heat equation. So it's very easy. Yes. Now what we do is we look at some boundary conditions. Okay, so what sort of equations are we talking about here? So let's look at some boundary conditions which we actually encounter here. Okay, so boundary, and for now let's just look at this problem only, one dimension. You see, in n dimension also same sort of boundary condition will work, but for now let's just concentrate on one dimension. Okay, so let us for time being concentrate on 1D heat equation. equation. Clear? Okay. Okay. And what we are going to do is we are going to write down the different boundary conditions which you can encounter here. Boundary conditions. Clear? Okay. What are the boundary conditions? So essentially you have this equation ut minus uxx equals to 0. But what are the boundary conditions? So before we look at the boundary condition, you can guess that we can actually we do have to define what the domain is. Yeah. But you see, I do not want to jump into a more complicated domain. Yes. First of all, let's do it for a one-dimensional thing, and we'll look at boundary condition, and then we'll go from there to a higher dimension. Yeah, that will make things easier because, to be honest with you, heat equations are a little tricky. Okay, it's not easy like a Laplace equation. Okay, so first thing first, let's write out a Dirichlet boundary condition. Okay, so essentially, I'm looking for this equation ut minus uxx equals to 0, one dimensional heat equation, right? And with this I am writing down the Dirichlet boundary condition. Dirichlet boundary condition. Okay, what is the Dirichlet boundary condition? Dirichlet boundary condition is essentially, you see, the x I am choosing it from, let's say, some 0 and t. Okay, 0 and t. Of course, t can be infinity. That's not a point here. But I'm just, for now, let's just say t positive and 0 t. X I'm choosing from 0 t. So Dirichlet boundary condition is u at 0 t, that is equals to u l t. Okay, this is equals to 0. So x I'm choosing from 0 to l. Clear? Okay. Oh, sorry. Here I shouldn't write x. This is t. Sorry, this is t. Yeah? I mean, of course, t can be, capital T can be infinity. Yes. I mean, you can just choose it for now. Just choose t between 0 and t, where t is positive. It can be in infinity also. Okay. And x, let's say for now, I'm just choosing x, between 0 and l. Yeah, and this is the Dirichlet boundary condition. So basically, it is saying u at the point 0 t equals to u at the point l t is equals to 0. So what it is saying is something like this. Let's draw some pictures here. Okay, let's say this is your x variable and that's your t axis. Okay, and 0 to l, that's your x, and 0 to capital T. So this is the domain where you are working with. Okay, this is the domain where we are working with, and in this domain u satisfies this equation. And what is the boundary condition? U for x equals to 0 and t equals to t, u at 0, sorry, u 0 t and u l t is 0. So essentially u 0 t and u l t. Okay, so on this line u is 0 and on this line u is 0. Clear? U0t equals to ULT equals to 0. So if this something like this happens, okay, then you of course have it is a Dirichlet boundary condition. The condition is called a Dirichlet boundary condition. Some idea of what heat equation looks like. Let us look at the n-dimensional general heat equation, yes, and how to work with that equation. So first thing first, n-dimensional heat equation. As you can understand, whenever I am talking about n-dimensional heat equation, I of course mean n is greater than equal 1. So essentially, whatever I am going to do, I am obviously, of course, one-dimensional heat equation is involved here. So again, let me write down what is n-dimensional heat equation. So in general terms, you can just write it like this. I mean, without any specific, notation. U ut minus ux1 x1 minus ux2 x2 minus uxn xn, this is equals to, let us say, a function which of course depends on x1 x2 xn, and of course you have this t variable, right? And this is defined in omega t. I will define what omega t is. Yes, these are complicated objects. Yeah, I have to define what omega t is. Or essentially, if you want to write it properly, yes, we write it like this. U t, generally speaking, we write it like this. Laplacian of u. So please remember this Laplacian is with respect to x, only the x variable, equals to f of x t. Okay, for x t in omega t. Okay, so that's your n-dimensional heat equation we have explained again. And what is omega t? Now here, omega t is very interesting. Yeah, what is omega t? See, as you know, whenever we say omega, what do we mean by omega? It's of course an open set, right? It's an open, smooth open set we are always considering. So here omega t, which is defined by omega cross 0 open t closed. Okay, this is omega t equals to this, yeah, where omega, okay, is an open connected smooth and bounded domain and t greater than 0 fixed. Is this clear? So what is omega? For now, you see, whenever I write omega t like this, yes, I mean this boundedness, I will explain to you when we need boundedness, when we don't. But generally speaking, this boundedness, so remark, generally speaking, boundedness is not required. Whenever it is required, I will just let you know. Okay, so maybe I can just remove boundedness from here. It does not, I mean, right now it does not matter. I will explain to you when we need. So let us just write down this domain and t positive. Yes, yes, boundedness is not required. See, boundedness we will assume later. Yeah, for now it is only this. So let us take up an example and see what this omega t means. See, essentially, what is omega? Omega t? Omega t is omega, which is an open set. Yeah, that's the important open set. So, of course, this connected, smooth, all this is included. But the important thing is omega is open and t lies between open 0, close t. Please remember this thing: open 0, close t. So, what does that mean? See, let's say that's your omega. Let us draw a nice omega. Yes, okay, that's a nice omega, and let us just do it like this. You see, let's say this is your this is the three-dimensional. Sorry, not the three-dimensional. This is the n-dimensional thing, right? So that is why. How do I put it? Maybe I can just. Maybe I can just. Sorry. Let me draw this thing first. Huh? So let's say this is your Rn space. Okay, not this direction. The whole this is your Rn plane, and that's your t direction. Clear? This is your Rn. So I mean, for intuition, let's just think that is your R2, right? This plane is R2, and that is the third dimension, which is the time dimension, and it starts from 0 to infinity. Clear? Okay, and in this thing, let's say that's your domain. And where is this domain? Omega. This domain is in Rn. I mean, for intuition, think of this as R2. Okay, so this omega is in R2, and then you have 0t, right? So 0t, something like this. The same thing will happen over here. Okay, so basically it is a can. Think of a can of a soda or something. Yeah, can of Coke or something. Yes. Okay, so omega t. Let's understand what omega t is. So omega t contains omega. So what is omega? See, here I drew it like this, but omega is whatever is inside, right? It does not contain the boundary. Okay. So omega cross 0t. So t, where is t0? In Rn, this on the base t is 0. Here t is 0, right? So basically this is t equals to 0. This is t equals to 0. And what is t here? T equals to t. Here equals t equals to t. So essentially 0 to 2 is this. See, what it says is, what is omega t? It contains, I mean, of course, does it contain this? So basically, think of this can. Okay, think of this can. Now, Does the base of the can, this base, is it included in it? Of course not. Why? Because t equals to base, it corresponds to omega cross t equals to 0, right? Does t, is t equals to 0 there? No, of course not. So the base is not there. Okay. So important thing is base is not included. Base is not included in omega t. Of course, it is true, right? Base is not included in omega t. Okay, let's just see that. So omega t is omega cross 0 t closed. Okay. Now, what about the top part? The top, the the lid of the can, yeah, or the cylinder, whatever you want to call it, huh? Is the lid included? So the lid means, you see, forget about this boundary. Yeah, that boundary is never included. But whatever the inside is, the inside lid, okay, is that included? T equals to T is included. So the upper lid, okay, how do I put it? The upper portion, yeah, you can just maybe the top portion actually, the top portion or the top is included. Let me write it included in omega t. Okay. Now let's see what else is included. Is this boundary included here? This boundary, clear? For t equals to 0, is this boundary included here? Of course not. Why? Because omega does not contain the boundary. Omega does not have any right on the boundary. It contains points in the interior. It does not have any point in the boundary. So boundary, you take any point on the boundary and t equals to 0 in this here, right? So basically that point is not included in omega t. So the boundary term, so this particular line, I mean this thing cos t equals to 0, and the sides, this thing, does it I mean, is it there in omega t? Of course it is not included in omega t. Okay. So the vertical sides, let me put it anyway. So this is important. Yes, the vertical sides, side, what I mean by vertical sides is the side of the can which you can see. So think of a coke, okay, those 330 ml coke bottles, okay, cans, the side of the cans which you can see from your eyes, that is not included is omega t. Okay, what is included is whatever is inside. Yeah, of course the base, is the base included? So think of the base to be, smooth base. It's not smooth in a can, but just think of that as smooth. The base is included? No, the base is not included. What about the boundary? Boundary is also not included. What about the side profile which you see from the side? That side, vertical side, they are not included. Are not included. Why it is not included in omega t? Because you see, any side, if you take any point on the side, what is it? It corresponds to some t equals to t1, and x is on the boundary of del omega. That is the sides, right? The vertical sides, and the omega does not contain the boundary, right? So the vertical sides are also not included in this. Okay, right. Now, so the top is included, the top part is included, vertical sides are not included, the bottom is not included, right? And whatever is inside, of course, it is included. So that is your omega t. Okay, right. Now we'll define another important property. So this is omega t. Let's say that is here, this is one. And we define, okay, so here, this is are the things which makes parabolic equation a little complicated. And we define a new boundary, a parabolic boundary, right? We define a parabolic boundary. What is parabolic boundary? We will write it like this, of omega t, of course, of omega t, which is given by is del omega t. Clear? That's your parabolic boundary. I mean, generally some books you will see it is written as del omega t, or in some books it is also written as gamma of t. Clear? And that is again defined by, so basically, I mean, this is not the definition, it is just a notation. It can be written as gamma of t, which is defined by, okay, omega t bar minus omega t. Just think about it. Okay, what does it mean? It means that you take the whole omega t, take the closure of that thing. Okay, the omega t is this in whatever is there, you take the whole closure. So now if you are taking the closure, okay, just think of omega t and think if you are taking the closure of that thing, what will happen? Think of that coke ball can, okay, it actually includes everything. So whatever is in the top, whatever is in the bottom, whatever is in the side, whatever is in inside, everything is included in omega t bar, right? Yeah. Okay. So the liquid along with whatever the surface you can see from outside, everything is included there. Now, what is omega t? As I have told you, omega t is whatever is inside and the top part, excluding these vertical sides and the bottom. Okay. So what is del omega t? If you just think of the parabolic boundary, the parabolic boundary consists of the bottom part, of course, and the vertical sides of omega cross 0 t. Okay, but not the top, not this part, not the top part. Okay, so it, let me put it this way: the parabolic boundary, okay, consists of the bottom and the vertical sides, okay, vertical sides of omega cross 0 t, close 0 t. Yeah, please remember this is close 0 t. Yes, of course, but not the top, that I explained, right? Not the top. Now, before we move on, I really want you to understand that what omega t specifically is. So take some points on the omega t or omega t bar, and just think about your. I mean, take some time, think where omega t bar or where omega t. I mean, which points are in omega t bar, which points are in the parabolic boundary. Clear? That is very important. And why is this important? Because that later on you will see that while we talk about maximal principles and all, it is very important to understand where the maximum is happening. Okay, so parabolic boundaries are very important to study. So let's say, for example, what I meant by this. Let's say you take a point here on the top of the point, t equals to t and x equals to some x naught, which is in the omega. Okay, do you think that point is there in the parabolic boundary gamma t? This is gamma t, right? Do you think it is in gamma t? Of course not. It's not there. Okay. What about this point? A point here. Okay. Do you think this point is on the parabolic boundary? Of course it is. Okay. That point is on the boundary. So let's say, so for example, let's put an example. Let's say this point. This point is x. Let's say this is x1 and capital T. Yeah. That is x1 and capital T. This point. So x1 and capital T. Okay, do you think that is on gamma t? Yeah, of course it is. Yeah, so this is in gamma t, but not in omega t. Of course it is not, right? I mean that is by definition of gamma t. Yeah, there. So, but of course it is gamma t bar. I mean that is always there. What about this point? Let's say there is a point here which is like a x naught capital T. Okay, do you think that point is there? So x naught capital T is not in gamma t, okay, but is in omega t. Clear? Okay. As you know that we want to study the well posedness of the n. So I will write it like this: n-dimensional heat equation. I will write it like this: n-dimensional heat equation. Okay. So please remember this thing. Whenever I write it like n heat equation, I mean the spatial dimension is in Rn. It is n-dimensional heat equation. Okay. So basically, our question is to talk. Our idea, what we want to achieve is to talk about know about well posedness of n-dimensional heat equation. Now, if you remember, if you want to study something like this, what are the things which you need to do? The first thing first, of course, yeah. But before we talk about well posted, of course, well posted of which problem? Let us put that first. Huh? So essentially, we are looking for this problem: ut minus Laplacian of u equals to f. As I told you, f depends on x and t, and this Laplacian is with respect to x, right? And this is in omega t. Okay, omega t is just the parabolic boundary. So you remember what is omega t? It is omega cross 0 t closed. Clear? T is greater than 0. For some t positive. Okay, so T positive, we are always. So I'm not writing all that every time. You do realize that T is always positive. Capital T is always positive, and this particular thing specifies the time variable. So ut minus Laplacian u equals to 0. And I will be talking about the well-posedness of which problem? The Dirichlet problem. As you remember, I talked about different boundary conditions, right? In one-dimensional equation, we talked about, Dirichlet problem, Neumann problem. So here I'm just generalizing this thing, and I want to talk about the well-posedness of Dirichlet problem. So how does that look like? It looks like U equals to G on gamma t. Okay, so which is omega t bar minus omega t. Okay, so the parabolic boundary. So is this clear? What am I saying? I am saying that I want my u to be equals to some function g. Of course, we want all of this to be continuous. Okay, to be some function g on the parabolic boundary, and such that u satisfies this equation in omega t. Clear? So whenever we say something is a solution, what do I mean by this? So let's write down the definition of solution. Classical solution. This is called a classical solution. Okay? Classical solution. So u in, this is a new notation. Okay, C21 omega t. Yes, C21 omega t. So essentially, if you remember what is, whenever we are writing something like, C1, C2, you remember what I meant by this thing, right? What do I mean? I mean that you are basically looking at Laplace equation, if you remember. Okay, we are basically talking about twice differentiable function Laplace equation, if you remember. Yeah. But here, what we are going to do here is, whenever we are saying that classical solution, we mean a u which is in C21 omega t intersection C omega t bar. Okay, so let me explain what I mean by this. C21 omega t is to this upper, the subscript or the superscript, sorry, this 2 that will represent the x variable. See, in earlier case, in the Laplacian case, there were only spatial variables. There was no time variable, right? It was not an evolution equation for Laplace case. So there was no, the two parties. So basically, there is no spatial and time variable, and hence you do not have to signify. C2 gives you everything. Here, you do not need two variables for in the time, right? You do not need twice regularity. So you do not need C2 with respect to time, because only ut is there, right? So you just need one derivative with respect to t. So that is why this is one derivative with respect to. So this will actually specify what the derivative is with respect to t. This will specify what the derivative is with respect to x. Okay, spatial variable. This is spatial, and that is the time variable. Omega t, of course, it has to be C21 in the whatever the domain is, omega cross 0t, because in this omega t only this has to satisfy equation. Okay, and for this equation to be satisfied, u has to be at least twice differentiable with respect to x and once differentiable with respect to t. That is what I wrote here. Okay, intersection C omega t bar. Intersection C omega t bar. See here, whenever I am writing all that, of course I am assuming that and if G are continuous, wherever they are defined, they are continuous. Okay, that is always assumed. Okay, so if G is assumed, you are basically saying that u is equals to a continuous function on the parabolic boundary. Okay, so I am assuming u is continuous on the boundary also, so up to the boundary. Okay, omega t bar. Clear? So that is what it is. So let's say if, let's call it 1. If u in C21 omega t intersection C omega t bar solves 1, okay, so basically that is ut, let me write it properly, ut at the point xt minus Laplacian of u at the point xt equals to f of xt, okay, for all xt in omega t, and u of xt equals to g of xt for xt in gamma t, which is the parabolic boundary. Okay, so this should hold for all xt, for all. Okay, and this should hold for all omega t. Then we say u is a classical solution of 1. Classical solution of 1. Clear? Then you say it is a classical solution of 1. Right. Now, once this is taken care of, now we want to talk about the well-posedness. Right now, I can talk about well-posedness. So, first thing first, what do you have to do? You have to find existence, yes, and then you have to do the uniqueness part. And then, after you do uniqueness, then the continuous dependence on boundary data. For now, we are just interested in finding the uniqueness. Clear? We are just going to do uniqueness. So essentially, so we are going to let me put it a small note kind of. This is not a remark; it is a note. We are going to use the same plan, the same. How do I put it? Plan maybe, which we used to study heat equation. Okay, Laplace equation. Let's say Laplace equation. So basically, first of all, in Laplace equation, if you remember, we started out with the uniqueness and then we went from there. Okay. So and here, let me again emphasize what is C21 is basically, it means twice differentiable with respect to x and once differentiable with respect to t. Clear? Okay. Now, so uniqueness. Let's talk about uniqueness and then we will go from there. Uniqueness. Okay. So we assume, for uniqueness we assume that omega subset of Rn is open. Of course, all of that is true. Open, connected. As you guys know that this is always assumed. Smooth. But this is the extra term which I am assuming for this. And bounded. And bounded. Okay. And bounded in Rn. Clear? Right. Now what we want to do is we want to talk about, so if you are taking omega like this, yes, we want to see if there is a unique solution. Let's say if we can solve the problem, does there exist a unique solution for that? And what sort of problem are we talking about? Let me write down that problem and then it will be more clear about what the problem is. Okay. So essentially the problem will look like, so consider the problem, or maybe I can write down the theorem first. That will be better, no? Let me write down the theorem first. Theorem. Okay, the theorem should be if there exists a solution, classical solution. Whenever I mean solution, I mean classical solution. Okay, so basically classical solution. Okay, u in C21 omega t. Okay, if there exists a solution, because we don't know if there is a solution, I'm just assuming that there is a solution. If there is a solution, okay, of 1, then the solution is unique. Is this clear? So it says that if there is a solution, it has to be unique. Yeah. Why I am doing it like this? Because we did not prove that there is a solution. Okay. So initially I was going to write that there exists a unique solution, but in that case, see, initially, so let me tell you this particular thing, so you should not do this mistake in the future. I was about to write the theorem like this, that there exists a unique solution of 1. If I write it like this, there is no harm in that. But the thing is, in that case, you have to show that there is a solution and then the solution is unique. Okay, I am not saying that. Please remember this thing. Here I am assuming that I am saying that if there exists a solution, so basically I am saying that you give me a solution. Yeah, once you give me a solution, I can tell you that whether it is unique or not. And in this case, it is unique. But the thing is, initially, I don't know whether there is a solution or not. Okay. So proof. Let's look at the proof of this thing. We'll actually prove all this, that how to find the solution and everything. Yeah. But for now, let's just assume that if there is a solution, it has to be unique. So let's say u and u tilde. This is our usual thing. Huh? U and u tilde are two solutions. You guys know, right? That whenever we want to find uniqueness, we start with two solutions. Okay, and you define w to be u minus u tilde. Okay, this is what you define. Now, once you do that, then you see the linearity kicks in. Since u and u tilde both satisfies this equation, what is the equation here? Both satisfies this equation. What will happen? That the u minus u tilde will satisfy the homogeneous problem. F is getting cancelled out here. Yes. So basically, let me write it. Ut minus Laplacian of u equals to f, and ut u tilde t minus Laplacian of u tilde equals to f. Okay. If you subtract it, basically what will happen is u minus u tilde with respect to t minus Laplacian of u minus u tilde equals to 0. So this is thanks to linearity. See, all of this is possible because these equations are linear. Now define w, which is u minus u tilde, right? Once you define something like this, then wt, okay. Oh, we did define w to be u minus u. Okay, so I defined it twice. Huh? I mean, yeah. Let's just not define it here. Huh? I will just define it here. I mean, it does not matter. You do realize that. Huh? It does not matter. Okay. So then wt minus Laplacian of w. This is equals to 0. Yeah. In omega t. And what about in the parabolic boundary? In the parabolic boundary, w is equals to 0 on gamma t. Again, the same thing happens, right? G and g gets cancelled out. So in the parabolic boundary, w is going to be 0. Okay, now set the new, this is the new thing. We set a E of t. This is kind of energy at the energy of the system at any time t. So this is defined by integral over omega. Please remember, this is not integral over omega t. It is the only integral over omega w square xt dx, because this is with respect to omega. X is in omega, t is in 0t, right? Et I am defining, this is defined for all t between 0 and capital T. So essentially what am I doing? I am taking any t between 0 and capital T, and I am defining energy with at that particular time given by integral of w square xt dt. Right? So if I do that, then what is E prime of t? Prime is with respect to t. Okay? The derivative. So that is equals to integral over omega. If you take derivative with respect to t, the t gets inside, right? Because this integral is with respect to x. So I can take it inside. It becomes 2 omega of xt omega t of xt dx. I hope all of you will agree with me here. Okay. So that is this is E prime of t. And you see, this will actually give you integral omega of xt. What is omega t? It is Laplacian of omega xt dx, right? Yes or no? Why? Because you see, omega satisfies this equation, right? So omega t is Laplacian of w. Sorry, I'm saying omega, right? Sorry. This is the, I mean, you can call it omega, you can call it w. I'm really very sorry for the confusion. So let's just call it omega, w, okay? And this is omega. This is omega, this is w. So I am taking the integral over omega of w square. Here, 2 integral over omega w wt, and 2, since w satisfies wt minus Laplacian w equals to 0, so it is equals to 2 times integral w Laplacian of w. Clear? Okay. Because wt is equals to Laplacian of w. Okay. So that is why I just wrote it like this. for any given t in omega. So omega cross t equals to t, let's say, there wt is Laplacian of w, right? Because it satisfies w solves the problem. So this is true. Now integration by parts, our usual friend, integration by parts. So that will give you integral over omega gradient of w square dx. Clear? That will give you, because you see, this is w and that is the integration will give you like a gradient of w square. One derivative will go here, it will gain one derivative, it will lose one derivative, that is becoming this, and there is a boundary term. What about the boundary term? The boundary term, w is equals to 0 on the boundary. W is 0 on the boundary. So there is no boundary term, right? And this is particularly always non-positive because there is a negative sign involved here, right? So this is non-positive. What does that say? Therefore, it says that what about E of 0? Let's look at what is E of 0. So E is defined in such a way that t equals to 0. Okay, it is w square x 0. Okay, for t equals to 0. So basically, you are looking at w on the base. On the base, this is 0 because the base is containing gamma t. So see, let me put it this way: E at the point 0, that is integral over w square x0 dx, right? Okay, x0 t equals to 0 is basically the base. That base is included in gamma t, yes or no? So w is 0 on the gamma t. So basically, you are taking the integral of 0, that is 0. Okay? Since x0 belongs to gamma t. Yeah, I hope this is fine because this is the bottom part of the lid, right? Of the can. Okay. So what do you have? You have e prime of t is non-positive, right? So that will give you e of t is less than equal e at the point 0, which is 0. Yes, for 0 less than t less than equal capital T. Yeah, this is true. Okay. So since E is, E prime is less than equal to 0, right? So therefore, what does that say? That says that, and you see, what is the definition? So by definition, again, by definition, you see, what is E? E is w square, integral of w square. So w square, whatever it is, w square is always greater than equal to 0, right? It's a positive function. I am taking the integral of a positive function. So this E t is always positive. So 0 less than equal E of t less than equals to 0 for all t between this. Yes, that will give you Et identical equals to 0. So hence E of t is identical equals to 0 for I'm writing this in too many times, t between 0 and t, capital 0 t. So Et is always 0. And hence, if Et is 0, what does that mean? Let's see. What is Et? Et is integral over omega w square, this function. This is equals to 0. So w is a continuous function, right? Because w solves the problem, so it's a continuous function. So you have a, w square, the integral is identical equals to 0. That will give you w square is identical equals to 0. That will give you w is identical equals to 0. It has to be, right? Yeah, because if it is positive, if w square is positive in some positive, in an open set containing omega, because, and then the total contribution of Et will be positive. Okay, that is not happening here. So hence, w, which is given by u minus u tilde, this is going to be 0. Okay, in omega t, which will imply u is u tilde in omega t. I hope this is fine. Okay, so there is a uniqueness here. Okay, now what we are going to do is, it is a time dependent variant. Okay, so essentially, I am just taking one fixed time and I am doing all of this thing and I am showing uniqueness. Okay, so basically, what did we prove? We proved that if you have an equation like this, what is the equation? The equation which looks like this. Okay, equation which looks like this: ut minus Laplacian u equals to f, u equals to g on the parabolic boundary. Then if omega is bounded, please remember this is for a bounded domain. If omega is bounded, then we can say that we can have a unique solution. if the solution exists at all.
Okay. So with this, we are going to end this